So welcome to Chapter 5, Ethernet. This is for my Introductory to Networking or my Fundamentals of Networking for a Cisco course. So this chapter we're focusing on our Ethernet technology. We're looking at the Ethernet sublayers, the frames, the MAC addresses. We're going to be describing what ARP is, how it works, how it impacts. We're going to talk about basic switching concepts, fixed configuration versus module. We're going to look at layer 3 and layer 2 switching. Our chapters are broken down into a basic introduction, Ethernet protocols, ARP address resolution protocol, LAN switching, and we're into the summary. So the first one is dealing with our Ethernet protocol. Ethernet protocol happens to operate between layer 1 and layer 2, and we're focusing heavily on our layer 2, which is our data link layer. That's where frames happen. And our data link layer is composed of two sublayers, an LLC and a MAC. LLC is our logical link control, and our MAC is our media access control. And our Ethernet helps define our layer 2 and layer 1 technologies and protocols. They dictate things like our bandwidth. And an interesting thing is, here, when we're talking Ethernet, it's not always about like the cable. It's about the communication and network technology standard that is defined by IEEE 802.3. That is the IEEE standard for Ethernet. So it operates at the data link layer, which we already talked about. It is the most widely used LAN technology in existence today. Graphical representation, again, 802.3 operates at the lower half of data link at the MAC layer and at the physical layer. So, two sublayers, what does that mean? The first sublayer, the LLC, handles communication between the upper and lower layers. It takes network protocol data and adds controlling information to help deliver packets or frames to the destination, because again, we're dealing at the layer 2, so we're not dealing with packets, we're dealing with frames. Our MAC address constitutes the lower layer sublayer of the data link layer. It's implemented by hardware, normally through some type of network interface card. It has two primary responsibilities: data encapsulation and media access control, or MAC. So here is our sublayer. Again, data encapsulation. That's dealing with our frame delimiter, our addressing, our error detection, our frame sequence checkers, our frame check sequence. It also then deals with the media access control, which is the second sublayer. And even though this is the media access control sublayer, that sublayer deals with the media access control, and that could be things dealing with things such as control of frame placement on and off the media, as well as media recovery. So we have highlighted that is where our Ethernet functions, and you're going to notice that we have different types of wiring: 10 base 5, 10 base 2, 10 base T, 10 base TXT, 10 100, 1000, base T, base ST, base LX, so forth. So there are numerous types of physical wiring standards. For our MAC sublayer, part of the data encapsulation, that deals with our frame assembly before transmission, as well as our frame disassembly upon receipt of a frame. The MAC layers add the header and trailers to the network layer PDU. That's our frame. It provides three primary functions: frame delimiting, addressing, and error detection, error checking. So our frame delimiting, it identifies a group of bits that make up the frame. That's going to be the synchronization between the transmitting and receiving nodes, essentially the start and end bits for our frame. addressing, that's going to be our source and destination MAC addresses. Also, error detection, it's going to double check that each of our frames have some type of CRC check to verify that the frames are without error. Also dealing with that is our frame check sequencer. Our MAC sublayer, the MAC portion that's dealing with the media directly, that's responsible for placement of the frame on the media as well as the removal of the frame on the media. It communicates directly with the physical layer. It deals with multiple device communication that includes things like collisions or corrupt or unusable data. And what's interesting here is where our Ethernet provides the controlling mechanism for shared access, and that is carrier sensing multiple access. And again, that carrier sensing, meaning that everyone is free to talk when they want to talk. So again, carrier sensing multiple access CCNA process. It is used to first detect if a media is carrying a signal. If no carrier is detecting, then you're free to transmit data. However, if two things are trying to talk at once, a collision may occur. Thus, a standoff time, which is a random time, is implemented between both nodes, thus allowing a break, thus preventing a collision or mitigating a collision. So this is contention-based access. If we have multiple nodes trying to share the wire, which that's perfectly okay, we just have to have a mechanism in place that helps control that. So again, that's going to be carrier sensing media access or multiple access, collision detection for Ethernet, collision avoidance for wireless. Moving on. So collision detection versus collision avoidance. Collision detection monitors the media and only transmit if the media is free. If by chance two things do try to communicate at the same time, then collision occurs, standoff period happens, and so forth. However, with collision avoidance, there will never be an opportunity free of wireless. So it's not so much it waits till there are no wireless involved, it's just going to try to wait to send when there's less noise. In a switch environment, using today's devices, CCNA CD isn't really necessary anymore because our collision domains are per port on a switch. Switches no longer clone signals and spew them out every port like a hub used to. So CCNA, collision avoidance, the device examines the media for the presence of a data signal. If the media is free, the device sends a notification across the media of its intent to use it, sends the data. It doesn't always mean that there is no signal. This could be a lower signal. So our Ethernet identity, we have a 48-bit address, or it's normally expressed as 12 hexadecimal digits. Normally it's broken up into two groups, our organizational unique identifier, our OUI, as well as our vendor-assigned NIC interface. So the OUI should be the same for all the manufacturer, and then it will just change the last 6 hexadecimal. So the frame processing, a MAC address is assigned to a workstation or anything with a network interface card. They're normally expressed as 2 hexadecimals, a delimiter, whether it be a hyphen or a colon, and there will be 6 pairs of hexadecimal numbers. So when a device is forwarding a message to an Ethernet network, it attaches the header information to the packet, containing the source and destination MAC addresses, because we're taking a layer 3 packet, we're packaging it to a layer 2 frame. Each NIC views the information to see the destination MAC address, and if the frame matches the device's physical MAC, it's stored in RAM. No match, the device discards the frame. Matches the destination MAC address of the frame, then the NIC will pass the frame up the OSI layer to the next layer. So it'll de-encapsulate the frame to a packet, and it'll verify IP address. That part's for a different chapter, but that's what happens. Here we have our earlier versions of Ethernet. That was our 10 meg. Now we can do 10 gig. And our Ethernet frame structure adds headers and trailers around the layer 3 packet or layer 3 PDU, thus encapsulating the layer 3 PDU, turning it into a frame. Ethernet 2 is the Ethernet frame format which is typically used in our TCP/IP networks. Even though we say Ethernet, it's a second evolution of Ethernet. So here we have our 802.3 and we have our Ethernet 2. You're going to notice they're similar. Here we have our packet. So our Ethernet frame size, both Ethernet 2 and 802.3 normally defines the minimum frame as 64 bytes and the maximum is 1518. So if it's less than 64 bytes, then it's considered a collision fragment or a runt frame and just ignores it. If the size is transmitted, the frame is less than the minimum or greater than the maximum, it drops the frame. However, we could have jumbo frames, and a jumbo frame can be over 9,000 bytes or bits. Bytes, not bits. Big B, not little b. So our Ethernet frame also has things like our VLAN information. So our 802.1q VLAN tag. That's going to be tagging information and a VLAN ID. So our VLAN ID, which is 12 bits, that's why we have the appropriate number of VLANs, because they're dictated by those 12 bits. So the beginning of our Ethernet frame, again, our preamble, that's the start delimiter. It's used for synchronization between our sending and receiving devices. The start, source information, our destination and source addressing. A length that defines how large the frame is. Our data, and that's going to be a layer 3 packet, and that's going to be encapsulated here. Then we will have our frame check sequence, and normally our end delimiter. There are 802.3, again, very similar. And our last part, our FCS, our frame check sequencer, is used for error checking. MAC addresses are in hexadecimal, so you have to understand hexadecimal. And again, hex, we're just really representing 4 binary bits with a single character. Here's an example of our MAC address. We've talked about unicast, multicast, and broadcasts, but now we have to go a little bit more in depth. Because again, this part right here is the data of our frame. They just are finally breaking it down into what the layer 3 packet looks like. Because this is really just a layer 4 segment and so forth. So with this, we're going to look at a unicast address. A unicast address is a 1-to-1. So it will be my source MAC address to a dedicated destination MAC address. And that's different from a broadcast, because a broadcast will be all Fs and that's a special MAC address that says send to everyone. Next is a multicast address. So first of all, our multicast addresses begin with a specialized value, 01005E in hexadecimal. That basically tells it that it's a multicast and it's going to be sent to a select group. Not to everyone, not to one-to-one, but one to many or one to a selective group. And then the destination, you'll notice, is a multicast address. So our MAC addresses are physical addresses. They don't change. Our IP addresses are logical, and they can change. MAC addresses, 6 pair of hexadecimal, 48 bits. Our IP addresses, let's assume IPv version 4, it's 32-bit of 4 groups of 8 bits that are logical. So part of our concept is this end-to-end connectivity, MAC and IP addresses. So a switch may examine our MAC addresses. If the appropriate MAC address does examine it, then it will pass it on to a layer 3 device. Our layer 3 devices process the IP addresses. So at the data link layer protocol, if we're trying to transmit between 2 locations, they're dealing at the layer 2 protocol. So they're only dealing with our MAC addresses. And what ends up happening is they'll peel off the MAC address as they jump. So this guy may send it here. This guy will peel off the MAC address of this laptop and we'll put its MAC address, we'll send it here, so forth and so forth. So what if we don't know our MAC address? How do we get it? We get this protocol called ARP, which is Address Resolution Protocol. And the purpose of ARP is trying to find the sending node has to have a way to find the MAC address of the destination of a given node or link. So ARP protocols provide 2 basic functions. It helps for resolving IPv4 addresses to MAC address, as well as maintaining a table 4 mapping. So, as an intro to ARP, if I need to send a packet to an IP address, but I only have the IP address, I don't know the MAC address of the device, I can send a broadcast asking who has this. And only the person that has the IP address should then respond. This will be sent as a broadcast. So the ARP table, this is a lookup table used to find the data link layer addresses that is mapped to a destination IPv4 address. It also works as the node receives frames from the media. It should record the source IP and MAC addresses, thus allowing for a mapping. Next, there are ARP requests. They are sent via a broadcast to all devices on the LAN. And anything that has a matching IP address in the broadcast should respond. All devices that have it that don't match the MAC address will just drop it. We can statically map entries based off of MAC to IP, vice versa. So here's our table building. So host A, its ARP cache at the moment has nothing. It could send a ARP request, and it starts slowly building it with the reply of the MAC information. And so it starts building its cache. And so it starts forwarding data with the MAC address information to the appropriate host. But as it starts learning more and more, it starts filling out its cache table. So ARP's role in remote communication. This is where it gets more confusing but important. If the destination IPv4 host is on a local network, the frame will be used the MAC address for the destination MAC. However, if the destination IPv4 host is not on a local network, it will have to use the source for the ARP process to determine the MAC address of our default gateway, the router. If in the event the gateway entry is not in the table, an ARP request is used to retrieve the MAC address of our default gateway. Here we go. In our ARP cache, after a certain amount of time, the host C network may be removed. If we're looking for a specific IP outside of our network, it will query via broadcast our router and get its MAC address. Here's our MAC address table on our router or on a PC that will show us our mapping of addresses to MAC addresses. So how ARPs can generate problems is their broadcasts. So they could flood local media. So if we have a switch or a shared media, that's a problem. If we have a hub or shared media, we mitigate it by using switches. We move away from hubs to switches. So let's move to our LAN switches. A layer 2 LAN switch, which is the most common, normally communicates using layer 2. So that's going to be our frames and MAC addresses. Because remember, it does forwarding selection based off of MAC addresses. Anything dealing with IP has to be done at layer 3. So the switch MAC address table, as it starts communicating back and forth within devices, it starts mapping MAC addresses into a MAC address table on the switch. So for example, if the PC1 sends a broadcast, it will go from PC1 to port 1. That's the cable that we're plugged into the switch. The switch enters the source MAC address and the switch port that received the frame into its address table. Because the destination address is a broadcast, it will broadcast it out all ports except for the one that it received it on. Then the destination device replies to the broadcast with a unicast frame addressed to PC1. That way it learns if PC1 wanted to talk to PC3, PC1 will broadcast, switch will get it, send it to both PC2 and PC3. PC3 will go, oh, that's my MAC address, and then it will respond via a unicast. But that way the switch learns the MAC address for PC1 and PC3. And the next time something happened with PC2, it'll learn that MAC address. That way it has the table. A broadcast could be prevented from the switch if the switch knows the information and has it obtained in its MAC address table. Duplex settings, this is going to be sending and receiving, or sending or receiving, full duplex versus half duplex, one at a time or both ways. Auto-MDIX, Auto-MDIX, I always say MDXI, and I always mean MDIX. This is where, if we're connecting like devices, we need to use a crossover cable. Auto-MDIX may fix it. So if we connect two switches with a straight through, if the switches support Auto-MDIX, it will switch one cable, one port, so that it will communicate. However, this is not a standard, so this is an issue. Normally, you use the appropriate cable for the devices. Like devices crossover, everything else straight through. Switch to switch, crossover. Router to router, crossover. Router to PC, crossover. PC to PC, crossover. PC to switch, straight through. Switch to router, straight through. Let's get into the way that our switches forward information. This is a good one. So switches normally store information or forward information in only a few ways: store and forward and cut through. Store and forward, the switch will receive the entire frame, then compute the CRC. Only if the CRC is valid, then the switch will look up the destination address and then will send it out once it receives all of it. Next is our cut through. Our cut through switching will forward the frame before it receives everything. As it starts getting it, it'll just start forwarding it out the appropriate port. So no CRC will happen at the switch if cut through is enabled. So fast forwarding switching, lowest levels of latency, it allows for immediate forwarding a packet after it immediately forwards a frame after reading the destination address, and that's normally cut through. Fragment free, that's going to be when the switch stores the first 64 bytes of the frame before forwarding, and most of the errors that happen deal with the first 64 bytes. We have two types of buffers on a switch: port-based and shared. So port-based, that will be in port-based memory buffering. The frames are stored in queries that are linked to specific ingress or egress ports, incoming or outgoing, versus shared memory. That's going to be for the entire device. One of the last major topics is this fixed versus modular configuration, as well as things like PoE. So PoE provides power over Ethernet, and that is power via an Ethernet port. So fixed port is just that. We have X amount of ports on a switch, and that's it. We have a thing called stackable, and that's where it takes multiple fixed switches, and we have special cable that allows us to stack them. So they logically will look like one giant switch, even though physically they may be multiple. Lastly, we have these modular switch devices, and they can range in size, but that way they can grow as you need them. They may have dual power supplies and dual controllers and dual just about everything, but that is because they're a higher level switch and normally operate at the distribution or core layer switch fabric. Next is our modules, things like our SFPs, mini GPICs, that may provide additional functionality. In our fixed port, we may have 2 or more SFP connectors, and they can be, depending on the SFP connector you have, you could do things like a SFP fiber connector on a copper switch. That SFP gives that fiber functionality, or copper depending on whichever one that we have. Next, we have layer 2 and layer 3 switching, because we do have a layer 3 switch, and that could be an entire layer 3 switch or ports that are layer 3 and other ports that are layer 2. A layer 3 device does path selection, so it deals with packets because it operates at layer 3. A regular switch operates at layer 2, and if it wants to do anything with a layer 3 device, it has to then communicate with it. Next, we have our Cisco Express Forwarding. So this is a new technology that comes with layer 3 switching, and there's two major components with our Cisco Express Forwarding, known as CEF. The components are what's called Forwarding Information Base, or FIB. It's conceptually similar to a routing table, Networking devices use this lookup table to make destination decisions or switching decisions based off of that lookup table. It's updated when changes occur in the network and contains all routes known at the time. Also, it has a adjacency table, which maintains layer 2 next hop addresses for all our fibs. Types of interfaces could be a logical ether channel. That's going to be a bundled multiple cables physically that are logically considered one. We could have a switch port, which is a layer 2 port. We could have a routed port or a non-switch port that is a layer 3 switch port. We could have a virtual port or a switched virtual interface, SVI, and that's not really a physical port, it's just a logical port, which we use for VLANs. Here's an example. We can set individual ports on a switch to have an IP address, which means it will be a routed port or a non-switched port. And luckily, that's it for our chapter 5. And that's it for our basic Ethernet functionality. Thank you.